Okay? You got a line? Everybody have a line on your paper? Ah, I forgot one thing. If it was in green, I have green. So here's green. This is the sun. The sun goes on the edge of the paper, like that. There's the sun. Okay, you can see in the front I put my sun here, but it should be in the middle. Oh, let's fold it this way. And we do this. There. Okay. You've just solved the zero energy Kepler problem. Okay? You have solved the zero energy Kepler problem. That curve you drew.
Which one?
Did you draw your curve here? So I'm going to do it for a second. There is the solution. That black curve is the solution. So I want to show you why that's true. Okay, so that's going to be about half the talk. Why is that the solution? Now, you can draw any line you want, straight line, and do this, and you've got a solution. Okay? So that's the first half of the talk. And then we'll go, okay, so the next half is like, why is that a big deal? Okay, so, great. So just a reminder of what we're doing. We're solving Q double dot is minus Q over Q cubed that we all call Kepler problem.
But isn't the sun should be in the same plane as the planet?
We'll get to that, Gil. We'll get to that. Yes, it should be. So I have to explain why I'm telling you you've solved it. And there's an energy, which is this. Now this is the energy. Okay, and if Arnold were here, he would say it's called Kepler's problem because Kepler never wrote it down. Kepler didn't write down differential equations. Newton wrote it down as far as I know. Okay, so let's do, so the next few slides, the next few blackboards are why this works, okay? So we're going to go to Newton in general. And we might as well do it in higher dimensions for now. Can you see, big enough? Everybody can see? In the back, you see? Okay. So this has an energy. I'm going to call this N for Newton. And the energy is the kinetic plus the potential. And there's a trick due to Jacobi, and it's usually attributed to Maupertuis. It's called the Jacobi-Maupertuis metric. So I'm going to make it another metric. So it's called form a new metric, which is the usual Euclidean metric times a conformal factor. That's a conformal factor. And this is, sometimes I'll call this term the kinetic energy. This kind of the kinetic energy is a school, so this is like kinetic energy. If you think about it, this is also kinetic energy, so it's a little strange. But anyways, this is the Jacobi-Maupertuis metric. Sometimes I'll put an E on it, but this is the only metric I'll be using. And where is it defined? On a domain where the conformal factor makes sense. Okay, so it's some domain of space, huh? Of RD. So maybe it has holes in it. So you've got a new metric, and then the theorem is, if I can fit it on one board. Geodesics for this metric, I'll call it Jacobi-Maupertuis at that fixed energy. So that's what this is, Jacobi-Maupertuis at this energy R. up to reparameterization. So the reparameterized versions, solutions to Newton's equations with energy E. Okay? And the converse. So any solution to Newton's equations with energy E is a geodesic for this metric. So you've turned the problem into a problem in Riemannian geometry, except you have to be careful. Any Franco question? Any? Okay, so I'm going to put a little asterisk here. You have to take special care as to what a geodesic means when the conformal factor is 0 or infinity. So and plus infinity, I didn't say anything about the smoothness of this, but in the Kepler problem, the potential has a pole. So you have to be careful there. Okay? So that's the principle we're going. So now I'm just going to do this for the Kepler problem. I'm just going to go through this. I'm just going to go through the algebra of this metric and explain why it's the same piece of paper we did. So here comes the scary part. Okay, we take up a little break in Salome. Okay. And that board becomes semi-usable, huh? Oh, maybe this one. Yep, good. That one's steady. Okay, so I'm just going to go through this algebra. So we're going to take the energy E. We're going to pick V for Kepler. There it is. And we're going to see what happens. So Kepler. V is 1 over the distance to the sun. I'm going to take E to be 0. So ds squared is, the 2 isn't going to matter. 2q dq squared. Okay. So the claim is that's isometric to this cone, this exact cone. So that's what I want to go through now. So I'm just going to do it simply in polar coordinates. So I'll write q. My q's in the plane, huh? This q's in the plane. So use polar coordinates. So the V is just 1 over R. Yeah? So now the ds squared, the 2 doesn't matter as far as geodesics. If you multiply a metric by a constant, it doesn't change the geodesics. So I'm going to get rid of the 2. So this is 1 over R, and now I'm going to rewrite this in polar coordinates. dr squared plus r squared d theta squared. So this is equal to dr squared over r plus r d theta squared. Okay, so now if I draw a cone in the back of my mind, I have a picture of a cone, and there's an expression for any metric on a cone, and it's of the form. I want to turn this into the form d rho squared plus constant squared times rho squared, and this is going to be a new angle that I'm going to call phi. Okay? So I'm going to turn this, I'm going to do change of variables to change this to this. Okay? And this C has to do with how open the cone is. It tells you how big the cone is. So there's a pretty clear calculus exercise. Let's do it. So dr squared over r is d rho squared. D rho is dr over to r to the half. You can integrate that. Rho is 2r to the half. Okay? So I integrate it. I want rho equals 0 to correspond to being at the sun, to r equals 0. So when I go through that, then if I reverse, rho squared is 4r, so r is 1/4 rho squared, and I've got my change of variables. So the Jacobi-Maupertuis metric here, I changed the dynamics. All right. So we've got this metric to be ds squared is d rho squared plus 1/4 rho squared. It's the same theta, okay? D theta squared. So this theta and phi, I'm going to use the same. The theta is going to be theta, okay? So to understand what's going on, set rho equal to 1, just to understand geometrically. That tells you that ds is 1/2 times 1 d theta, right? If I set rho equal to 1 here, that becomes a 1. So take the square root, this. So what's that tell you? It tells you once around, if I go out from the sun a distance 1 and make a circle, the length is 2 pi. I mean, the length is pi, right? The integral of ds once around is 1/2 times 2 pi is pi. So that's the thing you made, right? If I take, we can do it on paper if we want. If you take your little ruler and put it at rho equals 1 from the sun and do this, right? There's my circle. That's my circle of radius 1 about the sun. Okay?
The same with the complex map, z goes to z squared.
Yeah, it's the same thing. Okay. So that's the so I want to do this a little bit like we're going to move to what Gil just said, z goes to z squared. So that will give us an analytic way to solve it instead of just the paper. So one way to do this would be to invert what we're doing here. I think I'm stuck, but let's see. Give me a moment. This is the break. Take a moment. No. Okay, never mind. All right. So one way to so maybe a better way to think of this first is an equivalent way to do this particular cone. It's the cone. So the geometric way people would say that it's the cone over a circle of radius 1/2. The normal plane is a cone over a circle of radius 1. That's polar coordinates. And this looks just like R2, mod the action plus minus 1. So in other words, I take the plane and I consider this vector and its negative to be the same point. So I do that quotient, right? So how do you realize that quotient? You take the half plane, right? That's a fundamental domain, and then I connect this to this. So that's what that picture had to do. So so I'm going to call this the Kepler cone. This is the Kepler cone. Okay, so let's do analytically, let's get to where Gil was going. So what was my change of variables? It was rho squared is 4r squared. Something first. So any cone like this, any cone at all like this, I can make it flat by changing the angle variable. So what I can do is I can take this thing and I can say this is d rho squared plus rho squared d of theta over c squared. Okay, now I turn it into a flat metric. This is the standard expression in the Cartesian plane for a flat metric. But now, this new variable, this gives you a new variable, phi, is theta over c, and phi now varies between 0 and 2 pi
C theta.
yeah, c theta. And right? Did I do the, oh, I did the division wrong. I did the algebra wrong. This is c theta. Sorry, I did the algebra wrong. That's c, okay? All right, so there's the change of variables then is, for us, the cone factor is a half. So our change of variables is that, and phi is a half theta. All right? So if you do that in complex variables, rho squared e to the I phi is 4r e to the I theta squared. Okay? So that's the change of variables I did. So if my original, so back to Kepler, so Q is r e to the I theta in C, which is R2 in the usual way, x plus iy. And what I'm doing is a map Q goes to Q, which is 4Q squared. Okay?
This doesn't work for other energies?
No. Doesn't work for other energies. It does work for other power laws. But it doesn't work for other energies. So that's the so then the upshot is if you combine the so we can draw a little picture of this. Let's see if I have a hidden board here. So if we combine the Jacobi-Maupertuis theorem with the algebra we just did, what we get is the result that this map takes straight lines to solutions to Kepler's problem at zero energy. That's that you combine the Jacobi-Maupertuis at zero energy. You know what the geodesics are. We've written them down. You drew them on the paper. And we know what the change of variables is. So we know what the geodesics on this flat cone are. They're just straight lines. And then you just look at them in the quotient. So that's what you did with your piece of paper. And then we just apply this map. So we could draw a little diagram. Let's see if I have one. Yeah, I guess I put it here. So how am I doing? Over and a half through? Yeah, I'm past half. Okay. So we could kind of summarize what I did here. So this is just like, right, you could give this to your calculus students to do. It's fun to do. So let's summarize with a little picture that I have so far. Yeah. So this is the Kepler cone here. And then I identify this with C. And And then I have a map down to C, which is squaring. I guess it's 4 times squaring. And this, analytically, as an analytic space, R2 plus minus 1 is the same as C. They're the same thing. But they're different geometrically. So we took the straight lines here. We took the Kepler. So this is I don't know how a good way to say this. This is kind of a summary of what I did. This is the Kepler Cone. Here's the Jacobi map for twee metric. And then this is this quotient map, huh? So this is isometric with that quotient map. All right. So that's kind of the, I'll write it out one more time. Q goes to Q squared. The 4 isn't important, it just shifts where the, how far out the parabola is. Maps straight lines to parabolas with 0 as focus. And you get them all that way, okay? So these are the solutions to the Kepler problem, the straight lines. Okay, so that's the upshot of the computation that I did. And this particular map has another name. This is a map used in Levi-Civita regularization. So if you look at the formulas for Levi-Civita regularization, it's the same Q squared. So there's a way of getting rid of the singularity at the collision. That's due to Levi-Civita and other people, and it's this map plus some change of time variable. So it's really the same thing. Okay, so that's the, that should hopefully describe the piece of paper. Okay, so now I need to do something. Now I need to give you a reason that I did all this, and I need a glass. Okay, so what I'm going to do now is I'm going to talk a little bit about Boseman functions and what's called weak KAM, and I'll just do the best I can. So the motivation for all this work came from Hector Sanchez. So he works with someone named Persino, and Renato, is it Hector Sanchez Morgado? I mean, yeah, is that right? Hector Sanchez, I always forget how to, Morgado. So the buzzwords are weak, these are the buzz, like when you put something in the archive, you have to put the keywords in. Weak KAM and Boseman function. So Hector and I worked on a paper with Rick Mokel. It's on the archive. It has the words weak K. I think it has that word in it. But it's about certain minimization problems that come up in n-body. And Hector visited me no, that's not right. He went to San Diego. There's an international congress there, an AMS thing, and we had a discussion. And he wrote down the Boseman function for the Kepler problem associated to the zero energy solution that goes right into the sun. And this is the expression he wrote down. Hector wrote down this expression, S is 2 r to the half cosine theta over 2. He wrote that expression down. And it was 2 pages of computation, and I was having a hard time following it. Well, the point is, if you do it in these new variables, this is just rho cosine phi. That's what the expression is. Now his range, he took his range such that this thing was always positive. So if you do this in terms of Cartesian coordinates, it's just this. It's just the opposite value of x. So I was trying to understand what he did and understand. So that's where this talk came from. So I want to explain a little bit about that now. I'm going to let that float. Okay. So I have to tell you what the Hamilton-Jacobi equation is and a little bit about it. So the equation is, there's a time-dependent and a time-independent version. I'm going to do the time-independent version. And you just set h of q ds of q equal to a constant. So that's a time-independent Hamilton-Jacobi equation. And the solutions are related to, there's a relation that I could say it this, yeah, this is a good way to say it. Solve, let me do it in the Riemannian case. This is the easiest to understand. There's a relation between these solutions, the S's, and solutions to the Hamilton's equation at that level C. So, case of R2, I'll just do a simple case to give you a little idea of what's going on. And the H is just kinetic energy. I should write P's, but it's just usual kinetic energy. And I'll take the C to be a half. Then the equation just says the gradient of S is 1. That's what the equation, you can rewrite the equation says that. And the solutions, well, let me give you a few solutions. S is just X, huh? The gradient of X is, yeah? S is distance from the origin. There's another one. Yeah, and the level sets are circles. And if you, in general, let's do it generally. Set fairly general solution. I take any set, any closed set, and I look at S to be the distance, the Euclidean distance from my vector point Q to this set. Okay, there's my set C. Okay, so just you could take it. This is the case of the origin is the closed set. This is the case of the y-axis, and then that's going to be that's going to solve, but it's going to have singularities. This one has a singularity here, right? And also, if I look at solutions to Q dot equals gradient S of Q, those are all straight lines. Those are automatically straight lines. So in this case, the solutions are radial lines, yeah? In this case, the solutions are that. In this case, the solutions, you just move as quickly away from this object perpendicularly, yeah? That's what the solutions are. And the singularities have to do with conjugate points. So that's a flavor of Hamilton-Jacobi. That's an example of Hamilton-Jacobi. And if you want to read what it has to do with Hamiltonian dynamics, there's a beautiful book by Fatih that you can get online. He's currently on version 10. It keeps updating and it keeps being free. So there's a relation between solutions to Hamilton's equations with added things about variational methods. Okay, so that's what people call, that whole subject is what people call weak KAM. All right, so now I need to add the word, so that is the best I can do in 10 minutes for this. So we're going to talk a little bit about Boseman functions. So maybe my favorite example is the one that Chaussat wrote down in his talk yesterday. Is horocycles. In the what do you call it?
It's difficult to see the way.
Choose another marker.
Yeah.
Probably dead.
Oh, the marker's dead.
Yeah.
Thanks, buddy. Mejor?
Yes.
Okay.
Yes.
Okay, so let's look at the horocycles in the upper half plane. So what do they look like? They look like lines, Euclidean lines like this, huh? Those are the horocycles. That's one. The other ones are the other horocycles are circles tangent to the boundary. So one way to get them is take a geodesic. Here's the kind of canonical geodesic, the x-axis, and go up along the geodesic. So I'll call the geodesic, say, gamma of t. And I start from some origin point. And what I want to do is look at the distance function from Q to gamma of t. And I want to let t go to infinity. But if I let t go to infinity, this goes to infinity and the whole thing doesn't work. So I just renormalize it by the distance from here to here. I'm parametrizing by arc length, so this distance is going to be t. And then when I do that, so I'm going to subtract t. So where's that t from? The t is the distance from gamma 0 to gamma of t. That's what that t is. And when I do that, the level set of this function is going to be a big sphere, or a circle, or it'll be a hyperbolic circle, and then I let t go to infinity. And that's a Boseman function. So limit t goes to infinity, distance q gamma of t minus t. That would be the Boseman function of q associated to this line. Okay? So there's actually a ray. It's associated to that ray. I change the ray, I change the Boseman function. The level sets are these. You can compute it by hand. These are the level sets. So this is the Boseman function. And it's this. You want to choose a nice geodesic to make the computation. And they have to have special characteristics. So in the original case that Hector wrote down, well, in the Euclidean case, this would be the Boseman function for the ray that's just going along the x-axis. All right. And then this solves Hamilton-Jacobi. So that's a theorem. The Boseman functions solve the Hamilton-Jacobi equation. So they're kind of limits of solutions, yeah? Because we know that each of these solve. This is just a constant, so it makes sense that the limit solves, but there's something to prove. So that's the Boseman part. And then, right. So what I have to tell you is a little bit about the n-body problem, how we came into this, and a little bit more about minimization. So let's see. Should I leave him start in 5 minutes, stop, or should I stop now, or when should I
No,
start?
we started 15 minutes late. So you have,
Oh, I'm doing great, okay.
you have 20
So I'm gonna try to stop 10 minutes early, so I'll go for 10 minutes, okay. So, let's see, where am I going? Right. So I want to tell you a little bit about this work that I did with Hector and with Rick Mokel and how it relates to this Kepler computation. And then I want to do the fun stuff, which is go back to these pictures, huh? Okay, so, let's see. So just a few more words about the weak KAM. As far as I know, to formulate the whole business, you need a Lagrangian version of the Hamiltonian theory. Is that, would you agree, Renato? Yeah. Yeah. So there, of course, there's a Lagrangian version for the n-body problem. So you take in the n-body problem, you take the L is the usual kinetic energy minus the usual thing. Here's the formula for so you have a bunch of bodies. We just did 3. So there's a Q1 and a Q2 and a Q3. So there's a Lagrangian. Oh, we got the sign wrong, right? Lagrangian is kinetic minus potential, and that makes all the difference in the world. This is kinetic minus potential. Okay? There's a Lagrangian. That's a positive thing. And what you look for is global minimizers, globally minimizing curves. So you want extremals, gamma of t, q1 of t, q2 of t, q3 of t, extremals for the associated action principle. Oh, bad chalk, thanks. Bad marker.
You got both the blue and you got the red or
Blue one under your paper there, it's open.
the blue and red are open.
Thank you. They're probably dead now too, right? No? Okay. So one extremals such that right, there's an action associated to this thing, right? S of gamma, and the typical action principle, you fix endpoints. You want these to minimize the action over all paths connecting, say, gamma 0 to gamma of t, but you actually want more than that. You want it to happen for all t, so you want to define on the whole line for all t, and you don't care about the parameterization. See, I didn't say how long I take to get from here to here. I can take any amount of time that I want. Usually you specify the time. So any time interval. If you do this in Euclidean space, you just get the lines. If you do this in the cone that you built, you don't just get the lines. You get half lines. If you do this in the n-body problem, you get what are called this central configurations. So there's those famous things in n-body called central configurations. For the 3-body problem, they're the Euler equilateral triangles, and these the Lagrange equilateral triangles. So let me just cut to the chase here. These minimizers for the n-body problem are zero energy, are some of the zero energy central configuration solutions. So let me tell you one. If you solve the one-body problem, the Kepler problem on the line, one solution is going to go something like t to the 2/3. I think I got the power right. If you just take a ellipse, and I'm sorry, an equilateral triangle, and let it blow up at the rate t to the 2/3, that's going to be one of these minimizers. So the theorem that we prove is in a certain range of masses, that's the only minimizer of this type. In a certain range. So that's how I got into the whole business. So to end up, so that just gives you a taste of the paper that I did with Sanchez and Moco. So it was around this. One of the tools we used was the weak KAM business. What I wanted, even in the plane, right? Even in the plane, the Hamilton-Jacobi equation has singularities right here. This guy has a singularity, right? And those singularities have to do with focusing of rays. A bunch of rays came together here. So I just want to go back now to the Kepler problem and go back to minimization and non-minimization. So if you look, I'm going to draw my sun here. The sun is where I do the fold. You want to imagine the line going on forever, huh? When I do the fold, this guy minimizes. This is a global minimizer until it gets to that closest point. And once it gets to that closest point, you can just start, you can almost see it here, right? Because look what happened. It came in and it turned back, and now it's staying a bounded distance away. And certainly as I go up this way, it's better to just cut across, right? So this thing fails to be a minimizer right there. What is that? What do you think? Where do you think that corresponds to back in the usual Kepler problem on the plane? Where do you think that point is? There's a name for it. The perihelion. So that's exactly what Hector found also. These weak KM solutions fail to be smooth at perihelion. And that has to do with non-uniqueness. So we can also draw that. It's a little bit easier. All right, so that's one version. And then maybe, I've got 5 minutes left. The other thing that I was in, there's another whole half of my work that I was interested in this because of. That has to do with whether something minimizes or not when you hit collision. And when you use these variational methods to prove existence of solutions, it's very important to be able to say something cannot minimize if it goes to collision. That turns out to be, so it's called Marshall's lemma. Marshall's lemma says if you have a minimizer in the n-body problem, then it can't have a collision point in the time interval in the interior. So I want to show you how that works in the Kepler problem. So you can relate, there's a very simple relation, only at zero energy between this and the Jacobi-Maupertuis matrix. So they're basically the same thing. So I want you to imagine now that I went straight into collision, okay? So that's the planet dropping into the sun, yeah? At zero energy. So now the question is, can I keep going and still minimize? That's a geometric question. So suppose I have a geodesic, so that's what, remember I said the geodesic theory gets weird when the metric blows up. So suppose I come straight into collision. Can you think of any way to go out and keep minimizing? Can you think? So you go in, and I want you to go out and keep minimizing. So the answer is no. And the easiest proof is you just do it in Euclidean. Just draw the proof in the plane, huh? Just right in the plane. So let me draw the little picture in the plane. If I have a minimizer, so here's the sun. If I go into the sun, remember the Z2 action. No matter how I go out, if I go out this way, that's retracing my steps, remember? So say I go out this way. Well, going out this way is the same as going out that way, yeah, because of this Z2. But anyways, I can always shorten it, right? I just go here, that's shorter. So it doesn't matter how I leave, I can always make them. So there's a phenomenon that we're not used to in Riemannian geometry, phenomenon of inextendable geodesics. There's geodesics, they're minimizing, they end at a point, and there's no way to keep going, and they remain a geodesic. It's just impossible. So inextendable geodesics are intimately related to the fact that you can get rid of, you can prove there's no minimizing action solutions that have a collision in the interior. And that was crucial to get these variational methods to work. And it's time to stop. Thank you.
Thanks, Richard. Any
Yeah.
questions?
So now if this cone has a circumference larger than 2 pi,
Say
so
again?
the cone is circumference pi, no? If you have it larger than 2 pi, now you're going to have geodesics that
Yeah, exactly. So you can, that constant C, you can make cones over circles of any radius.
And is this going to have any implication for your model?
Okay, so I started out this whole road because this Marcel lemma that we've been quoting for 20 years, I never understood. And so I decided I would try to understand it by methods I can understand, so I started doing this. And I was able to build potentials for which the Marcel lemma fails. And in essence, what I'm doing is doing what you said. I'm building a potential. It's not the usual three-body potential. I build another potential, homogeneous of degree -1, with the property that there are minimizers that go right through total collision, and they continue to minimize. And the way I did it, in essence, is what you just observed about making that angle bigger than 2 pi. So that is useful. Yeah.
This Z goes to Z square is also interesting for non-zero energy, like they asked. It maps, central ellipses to Kepler ellipses.
Right.
And this, what you showed, is a special case. Well, central ellipses, but with no force. So it's just
Right. So did you hear what Gil just said?
This is Arnaud, a beautiful article in Notices, from the 80s or 90s, the 90s. He explained this general trick.
It works for all the Kepler solutions. It takes a solution to the harmonic oscillator to a solution to Kepler.
Yeah.
So if you have an ellipse centered there, it gets mapped to one with a focus there. This is solution to harmonic oscillator. This becomes a solution to Kepler.
The generalization for any power law with some other powers other than 2.
What's kind of fun is to try to do it for Q double dot equals minus Q over a different power. And then you get different powers here, huh? And they could be irrational powers, and then you kind of don't know quite what you're doing. Or at least I don't.
No, Arnold explained it. It's an article in Notices. He gave it's the first visit in the US. He gave a colloquium in the physics department in Berkeley.
Yeah.
And then it came out as an article in the Notices. Extremely beautiful. Explain this trick.
Christina?
The obvious question, what about in 3D, the Pustahelman regularization, right? So you go to quaternions.
Yes, yeah, so it's just not as pretty. But there were various talks on 3D in the morning. Holger and the other person whose name I forgot, the guy from England. Where are you? Huh? Yeah. So the algebra gets kind of messier. I mean, you could do the same. I mean, you can shoot, and there's nothing stopping you from doing this with quaternions, right? I mean, you can or Clifford algebra valued things, right? I mean, why not? For Kepler, we know all the solutions on a plane, right? So why bother? I mean, it's but if you've got perturbed Kepler or something else, but I haven't done it. I mean, I mean, the metric theory is exactly the same. You see, for Kepler, we know what the solutions are. So what that means in this language is, for the three-body Kepler, all these planes are totally GDs except spaces, yeah? And when you do this metric business, the Jacobi Maffer-Twee, what you get is your manifold would be filled up with things that look like these cones. And those would be the solutions on those planes. But if you perturbed it, I don't know what to do.
All right. Okay. There are no more questions. Thank you again.